All right, so let's talk about our digital world. Everything is usually just on or off, a 1 or a 0. Simple. But the real world around us, it's full of nuance, right? Lights that dim, sounds that fade. So how does the super simple binary world of digital control pull off these smooth analog experiences? Let's dive into this really fascinating illusion.
Really think about it. A digital signal can turn a light bulb on, or off, fully off. There's no dimmer switch built in. So how on earth does a massive digital billboard in the middle of a city display millions of vibrant, smoothly changing colors? It seems like it should be impossible with just on and off, doesn't it? Well, turns out there's a trick.
And that trick, that secret weapon, is called pulse width modulation, or as everyone calls it, PWM. It's a brilliantly simple yet incredibly powerful technique that lets our digital systems create these amazingly analog-like effects. Honestly, it's the secret behind so many things that we just take for granted every day. So what is it exactly? Well, PWM works by taking a digital signal and just flicking it on and off at an insanely high speed. Now, we're not changing the power of the signal at all. It's always either fully on or fully off. The magic is in controlling the timing, specifically how long the signal stays on versus how long it stays off in each little pulse.
And to really get a grip on this, we need to talk about the most important concept in PWM, something called the duty cycle. Just imagine you're flicking a light switch on and off so fast that your eyes can't possibly keep up. The duty cycle is just the percentage of time that the switch is in the on position during one of those super fast flicks.
Let's just put a slightly more formal definition on that. The duty cycle is the percentage of time a digital signal is on during one complete cycle. So a low duty cycle means the signal is mostly off, with just a little blip of on. A high duty cycle means it's mostly on. This percentage, this is the one number we're going to control to make all the magic happen.
And that brings us right to the magic trick, the PWM illusion. We're about to see exactly how changing this simple percentage, the duty cycle, fools our eyes into seeing all these different levels of brightness.
So let's start low with a 25% duty cycle. What does that mean? It means for every cycle, the signal is on for only a quarter of the time, and then it's off for the other 3/4. It's a really short pulse of on, followed by a longer period of off, just repeated over and over and over, incredibly fast.
And here's the result. Because this flickering is happening way faster than our eyes can actually process, our brain just kind of gives up and averages it all out. We don't see a blinking light. What we perceive is a steady, dim light that looks like it's at about 25% of its full brightness. Pretty cool, huh?
Okay, so what happens if we bump that up to a 50% duty cycle? Well, now the timing is perfectly balanced. The signal is on for exactly half the cycle, and it's off for the other half, 50-50.
And as you've probably guessed, our visual system does the same thing. It blends that rapid on-off flicker into what looks like a steady source of light. So what we see is a light at medium brightness, about halfway between fully off and fully on. It's a perfect example of how the duty cycle directly relates to the output we see.
All right, let's push it even further. 75% duty cycle. Now things are flipped from our first example. The signal is on for most of the time, 3/4 of the cycle, and it's only off for a tiny, tiny moment.
And the result? Our perception smooths it all out again, and we see a nice, bright light shining at about 75% of its maximum potential. So there you have it. We've just created 3 totally distinct brightness levels using nothing but a simple on-off signal and some clever timing.
Okay, so the theory is great, but let's see how this actually works in the real world. We're going to look at a super simple example using a really common tool for makers and engineers, the Arduino board. You can basically think of this as us building just one single pixel from a giant digital sign.
So the physical setup here is really simple. We've got an Arduino Uno, which is basically the brains of our little operation. Then we have a red, a green, and a blue LED. Each one has a small resistor hooked up to it, just to make sure it doesn't get too much current and burn out. And, crucially, they're all connected to special digital pins on the Arduino that are actually capable of producing these PWM signals.
Now, inside the Arduino's code, all the magic really comes down to this one command, analog write. Now I know, the name is a little bit misleading because we know we're still using a purely digital on-off signal. But the name is meant to describe the effect we're creating. What this command actually does is just tell the pin which duty cycle to use. And this table here shows exactly how it works.
See, the analog write command uses a number between 0 and 255. 0 means a 0% duty cycle, so fully off. And 255 means a 100% duty cycle, fully on. So if we want to get a dim red light, we send the value 64, which is about 25% of the way to 255. For a medium green, we send 128, which is exactly 50%. And for a nice bright blue, we send 192, or about 75%. The number you type in the code directly sets the duty cycle, which directly creates the brightness that we see with our eyes.
So, okay, we've seen how to dim an LED. That's kind of neat. But why is this so important? You know, what's the bigger picture here?
This quote here is just the beginning. Let's go back to that giant digital sign for a second. Every single one of those tiny dots, those pixels, is made of a red, a green, and a blue LED. By using PWM to independently control the brightness of each of those three colors, you can mix them to create over 16 million different hues. A little red, a lot of blue, some green, boom, that's how you get purple. PWM is also how those signs can automatically dim at night and then get brighter during the day to be seen in the sunlight.
And here's the really clever part. Those big signs use a very, very high PWM frequency, so they appear perfectly stable, not just to our eyes, but also to cameras. That's what prevents that awful flicker you sometimes see on TV. From creating millions of colors to ensuring a perfect image, PWM powers precise, efficient, flicker-aware signage. So now that you know the trick, where else might this powerful illusion be hiding in plain sight?